My name is Adam Toroff, and I'm a senior software engineer with the Office of the Clerk of the U.S. House of Representatives. If you aren't familiar with the House of Representatives, we are one of two chambers in the legislative branch of the U.S. federal government, one of three equal branches in the U.S. government. The Office of the Clerk is a nonpartisan staff office that exists to support the legislative operations of the House. We track legislation as it gets introduced, amended, voted, and possibly even become law. The House of Representatives is over 200 years old, which helps ground our perspective in the clerk's office as we build systems. We aren't chasing the latest shiny new thing. We're looking to build systems that last and preserve the legacy of the House of Representatives. The project I want to talk to you about today is called LIMS. It's our Legislative Information Management System, an internal application the clerk's office uses to track measures as they run through the legislative workflow and possibly even become law. LIMS captures data generated by the House that we share with our partner organizations, such as the General Publication Office and Congress.gov. Some of these actions get recorded and published both in print and online. Our project with LIMS today is a greenfield project to update a mission-critical application. Our primary concerns are capturing the data as it is generated on the House floor and in-house committees, capturing it accurately, correctly, completely, and then publishing it transparently with an eye to preservation. We have a lot of special cases that we track because our business rules are the House rules. We need to capture these actions if and when they occur, even if they are rarely performed. Additionally, House rules may change at any time, and we must be ready to adapt if and when they change. Our new project is just a basic modern stack using React, GraphQL, .NET Core, Postgres, Java, and Kubernetes. Many of the same tools that you're using in your project today. Our system design is built around CQRS, the Command Query Response Segregation pattern. The primary goal of CQRS is to segregate the data access reads versus writes. There are many reasons why you would want to use an architecture like this to vary the read model and the write model. Perhaps you're trying to optimize read performance over write performance. Perhaps you have two different data stores for read and write. Perhaps you're varying the security model of your reads versus your writes. Our goal with CQRS in our application is to split out the read logic from the write logic and enforce all of the business rules every time we perform an update. Our use of CQRS and LIMS allows us to enforce the separation of concerns by process boundaries. Our front end has very limited business logic and focuses primarily on the UX. The back end is where we put all of the business validation, all of the integration with our legacy system, and all of the efforts to maintain data integrity in our data store. It provides the single point of contact between our modern and legacy data. All of the integration between our front end and our back end is handled through GraphQL with a Hasura server. The problem we're trying to solve here is modernizing a legacy application that dates back to the 1980s in the mainframe era. It's been upgraded twice, and it's time to replace it with something new. Our goal is to run the system side by side and update the legacy system module by module until our replacement is feature complete. There's a lot of intricate dependencies in the application, both between modules and across business entities shared throughout the system. We want to maintain separation of concerns because an opportunity to rewrite such a critical system like this does not happen often, and we don't want to squander the opportunity. We want to do our best to disentangle the UI from the business rules, and we want to capture the business rules as cleanly as possible so we can audit them, we can verify them, we can debug them, and we can compare them against the House rules, the authority on what the business rules are for this application. Our goal is to build something that lasts. We're looking at products, tools, architectures, components that are stable, well-tested, widely used, robust, modern, and well understood. Our goal is to build a system that lasts. This is not a simple throw it away project where as soon as we ship, we never see it again. There are many projects out there that are very important, very useful, and even mission critical that have very short lifespans. Ours is different. Our project is specifically designed and built to last for many years, perhaps even decades. That's nothing to say anything about short-term projects, but our focus is decidedly different from many projects out there today. Our system architecture is fairly common. We start with a React front end. All of our reads and writes go to our GraphQL server, Hasura in this case. Our data store, our primary data store is Postgres. And we send all of our write requests through our .NET Core backend. The .NET Core backend also has the single responsibility for being the point of contact with our legacy application through a Java intermediate layer. Our use of CQRS extends into our database architecture. We start with schema separation, where we have two separate schemas in use. A public schema that we use for our views, and a private schema that we use for updating. Our front end sends all of our queries through Hasura, which goes directly against the database to query the views. All of the mutations go to our .NET backend, where we apply all of the business rules and all of the validations before updating our writable schema, our app schema. CQRS was a key part of our system design when we started this project. We started looking at GraphQL, and we decided that GraphQL was stable enough that we wanted to move forward. When we started using Hasura, we found that CQRS just emerged naturally from the way we structured our system. When we want to do our reads, there's no cost to set up query handlers like we have in other GraphQL servers. And we've set it up so that clients cannot mutate data through rogue updates. We've published the read schema through read-only credentials over views. So there's no possible way the front end could accidentally update the data using our setup. All of our writes go through our business layer, and those are configured in Hasura through custom actions. We also like that Hasura manages our interface contracts for us, and they're all published in the GraphQL schema. This allows us to restrict reads versus writes, and it allows us to do all of our authentication and authorization through JWT roles, which pass all the way down to our backend. Getting the stack set up took a little bit of work, and we started by building out our database schema. This is the key part of our architecture. We started with a database migration scheme, a database migration framework. And since we're already using .NET Core, we had EF Core scaffolding available to us, so we started using that, and we found it had no problem scripting out multiple schemas. So it let us build the kind of schema that we're trying to use to do the segregation for reads and writes. We wanted to manage the GraphQL schema incrementally as well, where each view had its own SQL source file. We wanted to keep the Hasura configuration next to it so we can manage them as a matched pair. This required us to come up with some custom scripts to manage the Hasura metadata, the actions.graphql and the actions.yaml file. To do the setup, we just have our bootstrap script clear out the Hasura metadata with the Hasura CLI and post the metadata as is when the stack launches. This is a simple operation for us, and it works well. We have one Hasura server managing a single application, and it's done as well so far. Hasura also generates mutations for all of the views that it manages, and we specifically want to ignore them. For now, we just ignore those mutations because we've locked down the read schema so that there's no possible way to do a mutation through those paths. We let Hasura query the views with the read-only role, and we force all of the writes to go through our actions for our mutations. We could find a way to hide these mutations, but for now, for this internal application, we found it best to ignore them and not worry about the fact that they're there. It's not really a huge concern. We've been using Hasura on this project for close to 3 years, and our biggest win so far is having Hasura as our API server. We use standard off-the-shelf components to integrate the GraphQL schema into our front-end and back-end stacks. We use a standard Yarn task to generate a GraphQL schema in our TypeScript implementation. And we manage our read layouts in SQL, a skill that all of our backend developers have at the ready. We did a little bit of work to do some integration on our .NET Core backend so that all of our Hasura mutations come in with the same data shape. And that simplifies development and writing new mutation handlers. One downside we have with this architecture is that if you look at the full stack, there's 5 or 6 different syntaxes needed to do integration. It's a minor annoyance, but it's just the nature of modern development. We have a polyglot stack, and polyglot stacks need polyglot developers. So far, we're using a mixture of TypeScript and C#. We're using GraphQL, we're using YAML, we're using SQL, we're using Java. It's not the greatest solution, but our focus is on shipping software. This would be a nice problem to solve if we were writing a master's thesis or if this was an open source project, but we're focusing on shipping software, and it's not ideal, but we're happy to live with it and move on. When we started this project, we used another GraphQL server, and we found that we needed to write read handlers for every query that we needed to support. And that just was a lot of time that wasn't really value added. When we started using Hasura, we found that just the configuration to read and write from a view saved us tons of time. And that's time that we need to spend on focusing on where we can add value, modeling our business rules, and supporting our customers. Hasura is great, but it doesn't solve every problem we have. There are still some data modeling challenges, but that goes mostly into how we're modeling our data. This is not a Hasura problem. We found that there were some queries we were running that were incredibly slow performing, and we needed to dig into the explain plan to figure out where the hotspots were. Fortunately, the Hasura console made that very easy to find, and it made it very easy to see where we were modeling our data wrong. Once we remodeled our data so that we were putting module-specific data in module-specific detail tables, performance went back to where we expected, and it's been fine ever since. So far, this was a one-time learning experience that we found with our initial data setup, and it hasn't come back since then. And we're very happy with the result. The product has been in production for a little over a year. We have 3 modules in use, and we are converting modules as we get time. So far, we had one change in priorities where we needed to stop what we were working on and work on a new application. We found that there was no issue using this architecture on the new application deployed as part of the same stack. We wrote a new front end, and everything just worked fine. We had a new front-end application where we wanted to get access to some of the data that we had in our database, but we didn't want to include a GraphQL client in that application. In that case, we used Hasura endpoints, and that exposed a canned GraphQL query without any of the GraphQL ceremony around it. So far, we found that the architecture works well with monolithic and microservice backends. We have a mixture of both. We haven't really finalized whether or not we're going to lean heavily on the monolithic direction or if we're going to spread our application down into microservices. And we're finding that using Hasura as an integration point means we don't have to think about that until we need to solve that problem. And going forward, we're just going to plow ahead and just convert more modules in our legacy application and keep going. And that's it. Thank you very much. If you want more information on the House of Representatives, I can direct you to www.house.gov. If you want more information on the clerk's office, you can find that at clerk.house.gov. And if you want to see what's going on right now on the House floor, you can use one of our applications, live.house.gov. If any of this sounds interesting, we have an open job announcement for a cloud engineer. And if you're interested in working at the House, there are many other opportunities working as staff at the House of Representatives. Thank you very much.